Chicago, 1904. On the bustling wholesale market of South Water Street, James L. Kraft, a young cheese merchant, confronted the immutable law that governed his livelihood and threatened his solvency. He watched as a once perfect 32-pound wheel of Wisconsin cheddar succumbed to the elements. The outer rind, meant to protect its valuable interior, was drying and cracking under the city's fluctuating humidity. Molds, the airborne adversaries of every cheesemonger, were beginning to establish a foothold on its exposed surface. This was not a unique event. It was a daily predictable disaster. For a wholesaler buying cheese at roughly 9 cents a pound, every ounce of dried, crumbled or molded product he had to trim away was a direct and painful financial loss. A single wheel could represent a loss of over 70 cents, nearly a full day's wages for a labourer at the time. Multiplied across his entire inventory and across every grocery store in the city, the economic leakage was staggering. This battle was not merely a matter of lost profit. It represented a fundamental flaw in the entire system of food distribution. The customer experience was a gamble, the product inconsistent, its quality a function of time, temperature, and luck. The story of how a single innovation would transform the global dairy industry, creating a product with a shelf life measured in months instead of days, begins not in the gleaming kitchens of a modern food conglomerate, but on the sawdust-covered floor of this Chicago warehouse. It begins with a logistical and biochemical problem, the simple, unforgiving, and costly reality of natural spoilage. The frustration Kraft felt was not just that of a businessman watching his assets decay. It was the dawning recognition of a system that was fundamentally broken, a technical challenge waiting for an industrial solution. The problem James Kraft faced was not one of isolated spoilage, but a systemic failure rooted in the very nature of his product. Natural cheese, specifically the cheddar varieties common in American markets, was a dynamic, biochemically active entity. Far from being an inert foodstuff, it was a complex matrix of milk proteins, primarily casein, trapping globules of butterfat and residual moisture. This structure was in a constant state of slow, enzymatic evolution, but it was also profoundly vulnerable to its environment. It was, in effect, a living system, and like any living system, it was fragile. This fragility manifested in several commercially catastrophic ways. In the heat of a summer warehouse or an unrefrigerated rail car, temperatures rising above 70 degrees Fahrenheit would destabilize the delicate butterfat emulsion. The fat would begin to liquefy and separate from the protein matrix, weeping out in greasy pools onto the cheese's surface in a process known as oiling off. This not only created an unappealing slick product, but also altered the texture, leaving the remaining cheese rubbery and bland. In the cold of winter, the opposite occurred. Low temperatures and humidity accelerated moisture loss, causing the casein structure to contract, tighten, and crack. The cheese would become hard, dry, and crumbly, difficult to slice and undesirable to eat. Compounding these thermal vulnerabilities was the constant, inexorable threat of microbial contamination. Every time a cheese wheel was cut, its interior was exposed to a host of airborne molds. These organisms, landing on the nutrient-rich surface, would rapidly colonize, creating unsightly and often unpalatable growth that had to be meticulously trimmed away. For a retailer, this meant that a 32-pound wheel of cheese was never 32 pounds of sellable product. It represented a depreciating asset, an object locked in a battle against time, temperature, and biology. The result was an item that carried exceptionally high risk for an aggressively low profit margin, making the concept of a national cheese brand a logistical and financial impossibility. This systemic vulnerability translated directly into a chaotic and deeply unreliable consumer experience. For a housewife entering a grocery store in 1905, purchasing cheese was a gamble. The piece of cheddar she bought one week, creamy, sharp, and flavorful, might be followed the next by a slice from a different wheel, or even a different section of the same wheel that was greasy from oiling off, or brittle and near tasteless from excessive moisture loss. The grocer, armed with a wire cutter and a scale, could offer no guarantee of consistency. The product's quality was a function of its age, its placement in a non-refrigerated storeroom, and its precise location within the original wheel. The concept of brand loyalty, the very engine of mass-market commerce, was therefore impossible. A consumer could not develop a preference for Wisconsin cheddar as a reliable product, because the name on the crate meant nothing by the time it reached the counter. The cheese sold in a Chicago grocery could be radically different in taste and texture from a cheese sold under the same name in Cleveland. This inconsistency created a powerful psychological barrier. For the average family, cheese was not a dependable staple to be placed on the weekly shopping list alongside flour or salted pork. It was an occasional risky purchase, more of a luxury item whose quality could never be assured. This lack of predictability represented the fundamental obstacle to cheese becoming a truly national, industrial-scale food product. While other foodstuffs like crackers from Nabisco or soup from Campbell's were building national brands based on the promise of absolute uniformity, that a box or can bought anywhere in the country would contain the exact same product, cheese remained stubbornly artisanal and anarchic. It was a local commodity, not a national good. Before any company could dream of selling cheese from coast to coast, it first had to solve a more basic problem: how to make one piece of cheese reliably the same as the next. The industry was not waiting for a marketing innovation. It was waiting for a technological one. By 1909, the daily financial hemorrhaging from spoilage had brought the business, J.L. Kraft and Brothers Cosest, to the brink of collapse. The constant battles against mold, oiling off, and dehydration were not just reducing profits, they were consuming the company's capital. The accounting ledgers told a story of a business model locked in a losing war with fundamental biochemistry. The small victories of a successful sale were consistently erased by the strategic defeat of unsaleable, spoiled inventory. For James Kraft and his four brothers, it was becoming clear that their role as middlemen, merely distributing a product whose integrity they could not guarantee, was a path to certain bankruptcy. This reality culminated in a decision that represented a fundamental pivot in their operational doctrine. It was an act of taking command and control over a situation that had been defined by chaos. Instead of continuing to absorb the losses inflicted by the unpredictable nature of cheese, they would seek to master it. The new directive was clear. They would move from distribution to manufacturing. The goal was not simply to sell cheese, but to re-engineer it from the molecular level up. They would attempt to create an entirely new form of the product, one designed specifically to solve the logistical problems that had plagued the industry for centuries. The objective was not to make a more artisanal cheese, but a more industrial one. The final product had to be perfectly uniform, its texture and flavor profile consistent from one package to the next. It had to be stable, capable of neutralizing the enzymatic and microbial processes that led to spoilage. Most critically, it had to be durable, able to withstand the temperature fluctuations of cross-country shipment and a long shelf life in a grocer's storeroom without refrigeration. Kraft and his brothers were no longer content to be merchants. They now saw themselves as inventors, confronting a technical problem that, if solved, would not just save their business, but create an entirely new market. The war against spoilage was about to move from the accounting ledger to the experimental kitchen. The first offensive in the war against spoilage began not in a purpose-built laboratory, but in the back of the small company building, in a kitchen retrofitted for experimentation. The raw material for these early tests was the very physical manifestation of their financial losses, the unsaleable remnants of their inventory, dried rinds, crumbled pieces, and odd-shaped ends of cheddar. Products that would have been trimmed and discarded were gathered as the base material. The initial hypothesis was elegantly simple, borrowed directly from the established science of canning and food safety. Heat, applied correctly, was the ultimate sterilizing agent. If they could heat the cheese enough to kill the molds and bacteria, they could halt spoilage indefinitely. The process itself was rudimentary, relying on equipment repurposed from other uses. Using a conventional meat grinder, the brothers first pulverized the cheese scraps. This step alone addressed the problem of inconsistency. By grinding together cheese from different wheels and of varying ages, they created a single blended starting material. This heterogeneous mass was then transferred into a double boiler, a common piece of kitchen equipment that allowed for gentle indirect heating. The objective was to raise the temperature slowly to the pasteurizing range, approximately 175 degrees Fahrenheit, a thermal threshold well understood at the time to be lethal to the microbial agents of decay. For the first few minutes, the experiment appeared to be a success. As heat permeated the ground cheese, the particles began to soften, lose their individual shapes, and flow together into a molten liquid. But as the temperature climbed past 150 degrees Fahrenheit, a catastrophic structural failure began to occur. The delicate emulsion that defines cheese, a complex matrix of casein protein trapping microscopic globules of butterfat, collapsed under the thermal stress. The heat broke the fragile bonds holding the fat globules and physics took over. This was not a controlled melt, it was a total separation. What they poured from the pot was not a uniform, creamy block of restabilized cheese. It was a disheartening and commercially worthless substance. A tough, rubbery mass of coagulated casein protein had settled at the bottom, swimming in a clear golden sea of liquid butterfat. They had successfully killed the bacteria, but in doing so they had completely destroyed the product. The experiment was a failure, but it was an invaluable one. It revealed with terrible clarity the true technical challenge they faced. The problem was not simply pasteurization. The central obstacle was how to apply sterilizing heat without inducing a total separation of the fat and the protein. They had not been fighting biology alone, they were fighting the fundamental chemistry of cheese itself. The failed experiment in the company's back kitchen was not merely a disappointing result, it was a definitive scientific verdict. What lay separated in the pot, a greasy golden layer of pure butterfat floating atop a tough, chewy mass of protein, represented a fundamental lesson in colloid chemistry. The team had set out to sterilize a product, but they had instead completely disassembled it. The simple application of heat, the trusted tool of pasteurization, had acted not as a preservative but as a solvent, breaking the very bonds that made cheese what it was. This was the moment the problem shifted definitively from one of industrial processing to one of molecular science. The analysis of this failure revealed a deeper, more complex truth about the structure of cheese. Natural cheese is not a simple mixture, but a delicate water and oil emulsion, a state of matter maintained by a microscopic protein scaffold. This scaffolding is built from complex protein clusters called casein micelles, which are linked together primarily by calcium phosphate bonds, forming a three-dimensional net that traps globules of fat and pockets of moisture. When heated above approximately 150 degrees Fahrenheit, this intricate casein network undergoes a catastrophic transformation. The proteins denature and contract violently, their structure tightening like a clenched fist. This contraction physically squeezes out the liquid butterfat and water they were holding. The emulsion was not just weakened, it was annihilated. This realization brought with it a terrible clarity. Simply melting cheese scraps together would never work. The structural integrity of the protein matrix had to be preserved, yet somehow made pliable enough to blend and reform. They had fundamentally misunderstood the nature of their objective. The goal was not to gently melt cheese, but to find a way to completely break down the original unstable protein structure, and then rebuild it into a new, heat-stable and perfectly uniform configuration. They needed more than a grinder and a pot. They needed a chemical agent, a mediator that could intervene at the molecular level to control the behavior of the casein proteins under heat. The search was no longer for a better heating technique, it was for a missing ingredient. This pivot turned the Kraft brothers and their small team away from the kitchen stove and towards the quiet, methodical world of scientific literature. The solution, they now understood, would not be found in tinkering with temperatures, but in discovering a substance that could chemically modify the casein itself, making it a willing participant in a new, stable emulsion rather than a victim of thermal collapse. The problem had been redefined. They were not just trying to make a more durable food, they were attempting to invent one. The period that followed the dawning comprehension of the protein problem was not one of inactivity, but of a grueling, systematic and ultimately futile campaign of empirical trial and error. For months, the company's experimental kitchen became a laboratory dedicated to proving a negative. The team, armed with the knowledge that a chemical key was missing, nonetheless attempted to circumvent the core problem through the meticulous manipulation of every other conceivable physical variable. It was a brute force assault on a problem of finessed chemistry, an attempt to find a mechanical solution to a molecular scale puzzle. First, they attacked the variable of the cheese itself. Perhaps the specific protein structure of the aged Wisconsin cheddar they had been using was uniquely resistant. They substituted it with young, high-moisture Colby, theorizing that its softer, less developed casein network and higher water content might prove more pliable under heat. The result was an even faster, more catastrophic separation, the fat breaking free in a matter of minutes. They then pivoted to the opposite extreme, grinding hard, low-moisture grating cheeses, postulating that their already partially denatured proteins might better resist further thermal collapse. But upon reaching a temperature of 160 degrees Fahrenheit, it too separated into a gritty protein sediment and a slick of clarified butter fat. They even experimented with Swiss cheese, hoping its unique bacterial cultures and propionic acid might have some stabilizing effect. It did not. The inexorable law of casein contraction held true across every variety. Next, they focused with obsessive precision on the process variables of heat and agitation. They abandoned the simple double boiler for more controlled apparatus, allowing them to chart temperature curves with painstaking accuracy. They tried slow heating, raising the temperature by only 1 degree per minute over a 2-hour period. They tried flash heating, attempting to shoot the mixture past the 150-degree separation point so quickly that the emulsion might not have time to break. They experimented with high shear mechanical agitators, hoping a violent, constant stirring action could physically force the fat and protein to remain blended. They tried gentle, slow, folding with custom-made paddles, hoping to avoid agitating the delicate structure. Each time, physics took over. Each time, the outcome was the same, a greasy, separated failure. By the winter of 1915, the accumulation of these failed experiments had reached a critical mass. The back room was no longer a place of innovation, but a graveyard of dozens of identical failures, each one a pot of rubbery protein curd swimming in liquid fat. Every failed batch represented not just a scientific dead end, but a tangible financial loss in wasted material, fuel, and man-hours. The project, born of a desperate need to solve a financial problem, was now becoming a significant financial drain in its own right. The conclusion was becoming stark and unavoidable. The problem of creating a stable, processed cheese might not just be difficult, it might be fundamentally impossible. The long winter of failed experiments had not been a series of unlucky chemical incidents. It was a rigorous, if unintentional, confirmation of a fundamental law. To understand why every single attempt at simple pasteurization had ended in the same greasy, separated disaster, one had to look past the kitchen equipment and into the invisible, microscopic architecture of the cheese itself. The enemy Kraft was fighting was not a matter of process, but of structure. This was not a problem that could be solved by better stirring or more precise heating. It could only be understood by deconstructing the product at the molecular level. Natural cheese is not a solid block of uniform matter. It is a highly ordered, semi-rigid gel, an emulsion whose integrity depends on a microscopic scaffold of almost unthinkable fragility. The primary building material of this structure is casein, the main protein in milk. These proteins clump together into spherical bundles called micelles, which in turn are linked together by a delicate mineral-based mortar of calcium phosphate. This forms a vast, cross-linked three-dimensional protein matrix. It is a microscopic net, and within its porous structure, it traps billions of individual globules of milk fat and pockets of water. The entire system, protein net, trapped fat and water, is held in a state of delicate but stable equilibrium, giving cheese its characteristic texture and sliceability. Applying heat to this system is not a gentle act of melting. It is a violent assault on the very bonds that maintain this equilibrium. As the temperature rises past 150 degrees Fahrenheit, or approximately 65 degrees Celsius, the thermal energy begins to systematically sever the weak calcium phosphate links holding the casein micelles together. The protein net begins to unravel. Simultaneously, the casein proteins themselves denature. They lose their complex, folded shape and aggressively bind to each other, contracting and tightening like a clenched fist. This violent contraction has one inevitable physical consequence. It squeezes out the materials trapped within the matrix. The fine, emulsified fat globules, no longer held in place, immediately coalesce into a liquid pool of pure butterfat. The water is expelled. What the Kraft brothers saw in the bottom of their pot again and again was therefore not a failure of technique. It was a demonstration of thermodynamic destiny. Once the protein matrix collapsed, the separation of the fat and the protein was not just likely. It was a physical certainty. They had set out to kill the bacteria on the surface of the cheese, but their method had resulted in the total annihilation of its internal structure. This terrible clarity revealed the true scope of their war. The enemy was no longer just the mold on the rind. It was the fundamental, unchangeable nature of the casein protein itself. This impasse, reached in the winter of 1915, represented more than a series of failed chemical experiments. It marked the point where an emerging industrial philosophy collided directly with the centuries-old artisanal one. The properties of natural cheese that the Kraft team identified as catastrophic flaws, its biochemical activity, its structural transformation under heat, its very unpredictability, were the exact same qualities that a traditional cheesemaker considered virtues. This was not a disagreement over process. It was a fundamental conflict over the definition of the product itself. In the artisanal worldview, cheese was an expression of place, season, and craft. It was meant to be a living food. Its slow enzymatic evolution during aging was not decay. It was maturation, a process that developed nuance, complexity, and character. The subtle variations from one wheel to the next were not inconsistencies. They were the signature of the maker and the unique conditions of a specific batch, a quality known as terroir. The work of the affineur, the expert in aging cheese, was to guide this natural process, not to arrest it. From this perspective, a perfectly uniform, unchanging cheese was not a triumph. It was a sterile and lifeless object, devoid of the very qualities that made it desirable. The industrial philosophy, as embodied by James L. Kraft, viewed this entire paradigm through the lens of a balance sheet. From his perspective, character was an uncontrolled variable. Maturation was a countdown to spoilage and financial loss. Variation was a synonym for unreliability, the enemy of brand identity and mass market scale. The goal was not to guide nature, but to master and replace it. The industrial ideal demanded the complete elimination of biological and enzymatic processes, substituting them with knowable, repeatable, and controllable chemical ones. The cheese had to be severed from its life cycle, transformed from a dynamic system into a static, inert commodity. The rubbery, separated curds in the bottom of the pot were therefore the physical manifestation of this philosophical war, the violent rejection by a natural product of an industrial mandate. The solution, when it finally arrived, came not from a new piece of equipment or a different heating technique, but from a single entry in the dry academic pages of a chemical journal. The shift from a mechanical to a chemical approach had led Kraft and his team to a systematic study of salts and their effects on protein suspensions. There, they encountered a class of compounds known as alkaline buffer salts, and one in particular, sodium phosphate. Its documented function in other food applications was to act as a dispersant, a sequestering agent. In the context of the casein problem, this was not just an interesting property, it was a potential master key. The hypothesis was as elegant as it was revolutionary. The catastrophic contraction of the casein network was caused by the rigid calcium phosphate bonds that held the protein micelles together. Sodium phosphate, the theory went, could stage a chemical intervention. When introduced into the system, it would perform a function known as ion exchange. The sodium ions from the salt would effectively trade places with the calcium ions holding the casein matrix together. This simple swap would break apart the rigid, heat-sensitive protein scaffold, but without the violent contraction. The casein protein, its calcium bonds replaced by sodium, would become far more soluble in water and lose its tendency to seize up and expel the butterfat. With this new understanding, the team prepared for another experiment. The process began identically to the dozens of failures that had preceded it. Salvaged cheddar, ground into a heterogeneous mass. But this time, a precise and critical addition was made. A small quantity of powdered sodium phosphate, representing just under 3% of the cheese's weight, was blended into the mixture. The mass was then transferred to the double boiler, and the heat was applied. The temperature gauge climbed slowly, reaching the critical threshold of 150 degrees Fahrenheit, the point of no return where every previous batch had collapsed. Then it climbed past 160, and then to the pasteurizing temperature of 175 degrees. In the pot, nothing separated. There was no greasy slick of butterfat rising to the surface. There was no contracting, rubbery mass of protein sinking to the bottom. Instead, the entire mixture had transformed. it yielded into a single flowing substance, a smooth, homogeneous, and entirely stable liquid. When cooled slightly, it possessed a velvety, creamy consistency, utterly unlike the gritty, separated failures that had filled the company's waste bins for months. Physics had not been cheated, it had been redirected. The sodium phosphate had acted as a molecular mediator, successfully disarming the casein protein's self-destructive reaction to heat. This was not simply melted cheese. It was a new material, re-engineered from its constituent parts. The seemingly impossible had been achieved. The smooth, homogeneous liquid in the pot was not merely a tactical victory over separation, it was the result of a profound strategic realignment at the molecular level. What had occurred was not magic, but a precisely executed chemical maneuver. The sodium phosphate had not acted as a simple ingredient, but as a sophisticated diplomatic agent, a chemical liaison dispatched to negotiate a truce between the warring factions of fat and protein. To understand its success is to understand the dual nature of the casein protein itself. The casein molecule is, in chemical terms, Janus-faced. It possesses two distinct personalities. One end of the long protein chain is hydrophilic, meaning it is chemically attracted to water molecules. The other end is hydrophobic, meaning it repels water and is consequently attracted to fats and oils. In natural cheese, these proteins are tangled and bound together into the rigid casein-micelle network by calcium phosphate crosslinks. This structure holds the fat globules captive in a physical cage, but when heated, it is this same rigid structure that contracts and violently expels them. The sodium phosphate's role was to break these chains and repurpose the protein for a new mission. The salt performed this function through a process of ion exchange, acting as what chemists call a sequestering agent. Its molecules systematically targeted and surrounded the calcium ions that served as the mortar for the protein matrix. By chemically binding to the calcium, the sodium phosphate effectively dissolved the rigid bonds holding the casein proteins together in their compact heat-sensitive form. The rigid protein network was dismantled, but gently, without the violent contraction that caused separation. The casein proteins, now liberated and far more soluble, were free to uncoil and expose their dual-natured personalities to the surrounding mixture. This was the critical moment. With the old structure gone, the freed casein proteins could finally perform their true function as emulsifiers. Their hydrophilic, water-loving heads turned to bond with the moisture in the mixture. Simultaneously, their hydrophobic, fat-loving tails grabbed onto the microscopic globules of liquid butterfat. Each individual protein molecule became a molecular bridge, a chemical handshake connecting a particle of fat to the surrounding water. Multiplied millions of times, this transformed the mixture from an unstable physical suspension into an entirely new, chemically interwoven, and incredibly robust emulsion. The puzzle was solved. The protein no longer fought the fat. It was now chemically, inextricably, and permanently bound to it. To understand the stability of the final product is to move beyond simple chemistry and into the realm of applied physics. The successful emulsification was not a passive state. It was an active and continuous process of molecular-scale crowd control, orchestrated by the phosphate ions. The genius of the solution lay not in merely dissolving the protein scaffold, but in fundamentally reprogramming the electrical behavior of every single casein molecule, turning them from a disorganized, self-destructive mob into a disciplined, orderly army. The mechanism was one of electrostatic repulsion. In their natural state, the clusters of casein proteins carry a net negative electrical charge. However, in the matrix of natural cheese, these negatively charged proteins are bound tightly together by positively charged calcium ions, which act as ionic bridges, effectively neutralizing the protein's tendency to repel each other. This is what creates the solid, heat-sensitive structure. The sodium phosphate, dissociating in water into sodium and phosphate ions, staged a chemical coup. The highly negative phosphate anions possessed a far greater affinity for the positive calcium ions than the casein did. They systematically surrounded and sequestered every calcium bridge, breaking the chains holding the casein network together. This act of liberation had a critical secondary effect. With the positive calcium bridges gone, each individual casein protein was now left with its original, unopposed negative charge. The entire population of proteins was now electrostatically identical. The result was a principle familiar to any student of physics, like charges repel. The proteins, which had previously been forced into a tight formation, now aggressively pushed away from one another, preventing them from clumping together and contracting under heat. The phosphate had not just broken the enemy's lines, it had given every soldier a reverse polarity magnetic shield, making it impossible for them to ever reform their ranks. This state of mutual repulsion was the key to creating the final, stable emulsion. With the casein proteins now fully dispersed and unable to reaggregate, their dual-natured structure was finally free to act. Each protein's hydrophobic tail latched onto a microscopic globule of butterfat, while its hydrophilic head faced outward into the watery part of the mixture. Each fat globule was now effectively encased in a coating of protein. Crucially, because the outward-facing heads of the proteins all carried a negative charge, the coated fat globules themselves were now negatively charged. They too repelled each other, preventing them from ever coalescing back into a pool of liquid fat. The result was a perfectly ordered system, suspended in a state of controlled electrostatic equilibrium. It was not cheese anymore. It was a new substance, engineered for absolute stability. The implications of this chemical breakthrough were immediate and profound. The achievement of a stable emulsion at 175 degrees Fahrenheit represented a victory on two separate but critically interconnected fronts. First, it solved the structural problem of separation. But second, and of equal importance, it finally allowed the original goal of pasteurization to be met. The very heat that had once annihilated the product now served its intended purpose, to destroy the molds, yeasts, and spoilage bacteria that were the agents of decay. The emulsifying salt had not just stabilized the cheese, it had made it strong enough to survive its own sterilization. The result was a product severed from the biological clock. Its shelf life was no longer a matter of days or weeks. It was now measured in months, a level of durability that was entirely unprecedented and could be achieved without any need for refrigeration. This dual triumph of stabilization and pasteurization yielded a third, and perhaps more powerful, industrial advantage: the complete liberation from the quality constraints of the raw material. James Kraft's original business had been held hostage by the inconsistency of natural cheese. This new process turned that liability into a strategic asset. The system did not require perfect premium cheddar as its input. In fact, it thrived on variability. Young, mild cheese, over-sharp aged cheese, dry ends, and crumble, materials that previously represented a financial loss, could now all be fed into the grinder. By deconstructing them to the molecular level and then rebuilding the emulsion chemically, all of their individual characteristics were obliterated. The final product was no longer an expression of its source. Its texture and flavor were not determined by the quality of a specific wheel from a Wisconsin dairy, but by the precise, repeatable formulation of the blend. A specific ratio of young to old cheese, combined with a measured quantity of salt and water, would produce a perfectly consistent result every single time. Waste was eliminated. Variability was conquered. The final product was not just uniform, it was programmable. Kraft had not merely found a way to preserve cheese. He had invented a system for manufacturing absolute consistency from a stream of unpredictable low-cost inputs. It was the industrial ideal made manifest. The victory in the company's back kitchen was total, but its scale was microscopic. The smooth, stable liquid cooling in the laboratory pot was not an end, but a beginning. It proved a principle, but a principle demonstrated in pounds could not yet build an empire measured in tons. The chemical war against spoilage and separation had been won. Now, a new and arguably more formidable conflict began: the war of production. The challenge was no longer one of chemistry, but of physics, logistics, and mechanical engineering. It was the problem of transforming a tabletop success into an industrial avalanche. Recognizing the monumental nature of his discovery, James Kraft moved to secure the intellectual territory he had just conquered. On December 21, 1916, he filed an application with the United States Patent Office. The filing, which would eventually become U.S. Patent 1186,524, was more than a legal claim. It was a formal declaration of a new industrial process. It methodically described the process of sterilizing cheese and an improved product produced by such process, detailing the critical role of heating cheese to 175 degrees Fahrenheit, and, most importantly, the use of an alkaline salt like sodium phosphate to maintain the emulsion. This document was the foundational text for a new industry. It codified the victory won in the lab and served as the strategic blueprint for the factory. With the process legally protected, the immense practical challenge of implementing it at scale became the central focus. The double boiler and hand-cranked grinder were artifacts of the laboratory, entirely unsuited for mass production. The goal was to process not 5 or 10 pounds of cheese scraps, but thousands of pounds per hour. No existing machinery in the food industry was designed for this task. Confectionery cookers were built for sugar solutions, not dense, protein-heavy masses. Canning retorts were for sterilizing sealed containers, not for processing a viscous, flowing bulk material. The molten cheese mixture was a substance with unique and difficult properties. It was thick, sticky, and had poor thermal conductivity, meaning it was prone to scorching if heated unevenly. A thin layer could burn against a hot surface before the center of the mass had even begun to melt. The conclusion was stark and unavoidable. If Kraft was to industrialize his invention, he would have to invent the industry's machines as well. The battle shifted from the chemist's bench to the draftsman's table and the machine shop floor. The problem now was to design a system that could continuously grind, blend, heat, and hold tons of cheese in a perfectly controlled state, preventing any part of the massive volume from burning, while ensuring every particle reached the critical 175-degree pasteurization threshold. James Kraft, the merchant-turned-chemist, now had to become a mechanical engineer, designing the very hardware that would allow his new substance to conquer the American grocery shelf. The translation of the laboratory patent into an industrial process required the creation of a factory floor that was, in itself, a single, integrated machine. The system was conceived in 3 distinct but interconnected stages, each engineered to solve a specific physical problem of scale. The first was the mechanical obliteration of the raw material's identity. The small hand-cranked meat grinder from the backroom experiments was replaced by industrial-scale grinders, massive units capable of processing over 2,000 pounds of cheese per hour. These machines, driven by powerful electric motors, used a heavy-duty auger to force the inconsistent mixture of cheddar scraps, rinds, and odd cuts through a series of progressively finer steel cutting plates. The objective was not merely to chop the cheese, but to reduce it to a uniform, granular feedstock, destroying any trace of its original shape, texture, or source. It was the first act of industrial deconstruction. From the grinders, this homogeneous mass was conveyed to the operational heart of the system, a battery of enormous 500-gallon steam-jacketed cookers. These were not simply large pots. They were sophisticated heat exchange vessels designed to overcome the central challenge of heating a thick, viscous, and poorly conductive substance without scorching it. A direct flame would have created a burnt layer at the bottom, long before the center reached the required temperature. The steam jacket, a hollow shell surrounding the main kettle, provided the solution. Low-pressure steam, precisely regulated at 15 pounds per square inch, was injected into the jacket, creating a uniform heating surface of approximately 250 degrees Fahrenheit that enveloped the entire mixture. Inside the cooker, heavy, slow-moving scrape surface agitators constantly folded the material, ensuring that no single particle remained in contact with the hot wall for too long, while guaranteeing the even distribution of the emulsifying salts. This apparatus allowed the entire 500-gallon batch to be brought to the critical 175-degree pasteurization threshold with absolute uniformity. Once the molten cheese was fully emulsified and sterilized, the final stage began, the transformation from a liquid chemical product into a solid commercial unit. At the bottom of each cooker, a wide-mouthed 2-inch diameter pneumatic valve opened, allowing the thick velvety liquid to flow into a manifold. This casting machinery was designed for precision and speed. A series of nozzles dispensed a precisely measured volume of the molten cheese into standardized molds, moving along a conveyor belt below. These molds, typically made of tinned steel, were shaped to produce the now familiar 5-pound rectangular loaf. This process had to be rapid and clean, filling each mold in a single continuous pour to create a perfectly homogeneous block with no air pockets or seams. These 3 stations, the grinder, the cooker, and the casting line, were not merely separate pieces of equipment. They represented a single, continuous mechanical argument. The grinder erased the past. The cooker enforced a new chemical reality. The casting line dictated the final, uniform shape. This was not the quiet, patient work of an artisan guiding a natural process. It was a loud, hot, and relentlessly efficient system for manufacturing consistency out of chaos. The output was a substance of predictable weight, texture, and stability, a product no longer bound to the farm or the dairy, but created entirely by the logic of the factory. The industrial system of grinders, cookers, and casting lines described in the patent did more than manufacture a consistent product. It fundamentally re-engineered the economic ecosystem of the entire cheese industry. Its most profound and immediate impact was not on the consumer, but on the supply chain. The process created a powerful new industrial advantage by completely redefining the concept of waste. For every other cheesemaker and wholesaler in America, a significant and unavoidable portion of their inventory was destined for the garbage barrel. This was a simple, brutal law of their business. Rind trimmings, cosmetically imperfect pieces from a cut wheel, underweight sections that were difficult to sell, and cheese that had dried or discolored represented a constant and unrecoverable drain on revenue. This was not a minor issue. It could amount to a loss of 10 to 15% of a given wheel's weight. For a company handling thousands of pounds of cheese, this translated into tons of unsaleable product that had been bought, shipped, and stored at full cost, only to be discarded. It was a line item of pure loss. James Kraft, however, now viewed this material through the lens of his new technology. Armed with a process that could deconstruct and rebuild cheese at a molecular level, he was no longer dependent on aesthetically perfect, premium-grade inputs. The grinders obliterated physical imperfections, and the emulsifying salts neutralized textural and flavor variations. As a result, Kraft and his agents began to systematically approach other cheesemakers across the Midwest with a novel proposition. They would buy their scrap. They would purchase the trimmings, the offcuts, the crumbled pieces, the very material that represented a financial liability to everyone else. This was a strategic masterstroke. Kraft was able to secure a vast and continuous stream of raw material at a fraction of the cost of whole, first-quality cheese. Where a competitor saw a pile of trimmings representing a 30% loss on a given wheel, Kraft saw 100% usable feedstock, acquired for pennies on the dollar. A liability on every other cheesemaker's ledger had been converted through chemistry and machinery into a strategic high-margin asset for one. Kraft was no longer just in the cheese business, he was in the business of profiting from its inherent imperfections. With the challenges of chemistry and production solved, James Kraft opened a new, decisive front in his industrial campaign. The objective now was not the molecule or the machine, but the mind of the American grocer. The marketing strategy that would place his £5 loaf on every shelf in the nation was not built on the promise of superior flavor or artisanal heritage. It was built on a cold, direct, and overwhelmingly persuasive appeal to the retailer's balance sheet. Kraft was not selling cheese, he was selling a logistical and financial revolution. To understand the power of this strategy, one must adopt the perspective of the average American grocer of 1917. For him, natural cheese was a source of constant low-grade anxiety. A 32-pound wheel of cheddar represented not just an item of inventory, but a depreciating asset with a high and unpredictable rate of loss. His daily routine involved the meticulous trimming of mold and dried rinds, a physical act of cutting away his own profit margin. He contended with customer complaints about inconsistent flavor, and he watched his inventory oil off in the summer heat. Every ounce he trimmed and discarded was a direct financial loss, turning a product with an already thin margin into a high-risk gamble. Into this environment of chaos and loss, Kraft's salesman arrived with a product that was less a foodstuff than it was a packaged solution. The £5 foil-wrapped loaf was a tangible promise of command and control. Its benefits were not framed in the language of the gourmet, but in the language of the accountant. First was the promise of absolute stability. The product was pasteurized and chemically inert, its shelf life measured in months, not days. It did not require refrigeration, and it would not spoil. Second came the guarantee of safety and uniformity. Pasteurization meant the grocer could assure customers of its wholesomeness, a powerful selling point in an era increasingly concerned with foodborne illness. Consistency meant an end to customer complaints. The last slice of the loaf was identical to the first. The ultimate argument, however, was financial. The Kraft loaf eliminated waste completely. There was no rind to trim, no mold to cut away, no unsaleable dried ends. For the first time, a grocer could purchase 5 pounds of cheese and sell a full 5 pounds of cheese. The profit on the item was no longer a speculative estimate. It was a mathematical certainty. This transformed cheese from a high-maintenance, high-risk variable into a simple, predictable, high-turnover commodity. The narrative was not about taste. It was about the elimination of loss, the standardization of inventory, and the rationalization of profit. This was a weapon designed not for the consumer's palate, but for the logistical and economic realities of the retailer. The 5-pound loaf presented to the grocer in its gleaming metallic sheath was far more than a new form of cheese. It was a meticulously engineered logistical solution, a physical manifestation of the industrial doctrine that had created it. The innovation was not just the pasteurized product within, but the packaging and geometry that contained it. This was where the final battle against inefficiency and unpredictability would be won, not in the factory, but on the loading dock, in the storeroom, and at the retail counter itself. The first layer of this solution was the wrapper. Natural cheese was protected by a permeable wax or cheesecloth rind that slowed, but did not stop, moisture loss and microbial assault. Kraft's loaf was encased in tin foil, a material choice that was both symbolic and functional. At the time a novel technology for food preservation, the foil was a manufactured impermeable barrier. It completely arrested the exchange of moisture and air with the environment, physically guaranteeing the chemical stability achieved in the cooker. It was sterile, modern, and projected an image of scientific cleanliness. The wrapper was not just a container. It was a declaration that the product inside was no longer a part of the natural world of decay, but a creation of industry, sealed off and perfected. The second innovation was the loaf's shape. For centuries, cheese had been made in wheels, a form dictated by the craft of pressing curds. But the circle is a geometrically inefficient form for packing and shipping. Crates of cheese wheels contained vast pockets of useless empty air between the curved edges. The Kraft loaf, by contrast, was a rectangular prism. This seemingly simple design choice was a stroke of logistical genius. Rectangles stack with perfect volumetric efficiency. In a shipping crate, on a rail car, or on a storeroom shelf, there was no wasted space. The geometry of the product itself represented an attack on waste, maximizing the value of every cubic inch of transport and storage. The circle, the shape of the artisan, had been replaced by the rectangle, the shape of the factory. The result was pure efficiency. Finally, the loaf rationalized the act of sale itself. A grocer cutting a portion from a 32-pound wheel performed a small act of geometry, estimating the size of a wedge to meet a customer's request for about a half-pound. The process was slow, imprecise, and produced awkward, hard-to-sell end pieces. The 5-pound loaf eliminated this ambiguity. With a simple wire cutter, the grocer could slice off a perfectly uniform, rectangular slab of a consistent thickness. The sale was standardized. A half-pound was now a specific, repeatable dimension, delivered in seconds with minimal skill. And because the loaf was homogeneous and protected by its foil, the last slice sold was identical in quality to the first. There was no rind to trim, no dried end to discard. The 5-pound loaf was a calibrated instrument of commerce, designed to eliminate loss, standardize transactions, and transform the chaotic art of selling cheese into a predictable industrial science. The industrial perfection of the 5-pound loaf was a solution designed for the American grocery store. But in April of 1917, an event 4,000 miles away would provide the invention with its first and most demanding industrial-scale test. With America's entry into the First World War, the United States Army confronted a logistical challenge of unprecedented magnitude. How to feed a multi-million-man army deployed across an ocean, fighting in the static, squalid conditions of the European trenches. The Quartermaster Corps was not merely buying food. It was procuring advanced material for a new kind of industrial warfare, and the specifications for that material were brutally demanding. The search was on for a specific category of ration, a high-energy, high-protein item that could survive the journey to France and weeks of storage in a forward depot without refrigeration. It needed to be nutritionally dense, offering maximum caloric value for minimum weight and volume. It had to be safe, free from the pathogens that thrived in the mud of the Western Front. Finally, it needed to be durable and ready to eat, capable of being carried in a soldier's pack and consumed without cooking. Fresh meat was an impossibility. Canned salted meats were heavy and hydrically demanding. Natural cheese, the very product Kraft's invention had been designed to replace, was a logistical non-starter, guaranteed to spoil, mold, and separate under the harsh conditions. It was into this clear operational void that Kraft's processed cheese fit with the precision of a machine part. Its engineered attributes read as a direct answer to the Army's procurement checklist. It was pasteurized, guaranteeing its safety. It was chemically inert and shelf-stable, requiring no refrigeration. Its high concentration of protein and milk fat made it exceptionally calorie-dense. To meet the specific military requirement, Kraft abandoned the £5 retail loaf and developed a new form factor, a small 4-ounce cylindrical tin. This rugged, hermetically sealed, single-serving container was the final piece of the logistical puzzle. The product was no longer just a grocery item. It was now a strategic ration, a piece of food technology perfectly calibrated for the modern battlefield. The United States government would soon become its single largest customer. The initial government orders did not represent an incremental increase in business for J.L. Kraft & Brothers Co. They represented a complete industrial realignment, an event that would elevate the company from a regional innovator to a national strategic asset almost overnight. The United States Quartermaster Corps, responsible for feeding the American Expeditionary Forces, did not place a small test order. It committed to a scale of purchase that dwarfed the company's entire previous history. In total, the US government would procure over £6 million of Kraft's processed cheese for the war effort. This figure, translated into the Army's specified 4-ounce tins, meant the production of over 24 million individual hermetically sealed units of food. For a company that had, just a few years prior, struggled to process a few £1,000s a week, this represented an almost incomprehensible demand. The contract was not just a sale, it was a state-sponsored mandate for industrial expansion. The guaranteed revenue stream provided the capital to finance new factories, purchase fleets of steam-jacketed cookers, and establish a production infrastructure on a scale that private commercial risk would have never permitted. The war effort effectively underwrote the creation of the modern Kraft company, transforming it from a speculative enterprise into a major industrial player in less than 24 months. The logistical trial that followed was more brutal and more conclusive than any laboratory test. These millions of tins were shipped across a U-boat-patrolled Atlantic, unloaded onto the chaotic docks of French ports, and transported by rail and truck to forward depots. They were stored in damp, unrefrigerated cellars and carried for weeks in the rucksacks of soldiers in the mud-filled trenches of the Meuse-Argonne. In an environment where other foodstuffs spoiled, molded, or became inedible, the small tins of processed cheese performed with monotonous engineered perfection. The product's integrity was absolute. It demonstrated under the most unforgiving conditions imaginable the total victory of industrial chemistry over biological decay. The ultimate impact, however, was psychological, and it was directed at the nearly 2 million American soldiers who consumed the product. For the doughboy in the trench, the Kraft tin became a known quantity in a world of lethal uncertainty. It was a consistent, safe, and calorie-dense source of protein and fat that tasted the same in France as it did in a training camp in Kansas. This was not a marketing campaign. It was the largest and most effective product sampling program in history conducted by the US Army. An entire generation of young men, America's future consumers, were being conditioned to a new kind of food, uniform, durable, and branded. When these millions of men returned home, they brought with them a deep subconscious familiarity with a product that had been for many a literal lifesaver. To truly understand the strategic value of those 24 million tins, one must look past the nutritional tables of the Quartermaster Corps and into the sensory experience of the individual soldier. For the American doughboy mired in the alien landscape of the Western Front, the war was not an abstract strategic contest. It was a relentless, physical, and psychological assault. The environment of the trenches was a totalizing sensory shock. The constant percussive thud of distant artillery, the metallic odor of cordite, and the pervasive, inescapable smell of mud, damp wool, and decomposition. The food itself, hardtack biscuits, tins of tough corned beef, and weak-boiled coffee, was monotonous, unfamiliar, and often unpalatable. It was a diet of pure, joyless subsistence. Against this backdrop of lethal chaos and sensory deprivation, the act of prying open a 4-ounce tin of Kraft cheese became a small but powerful ritual of order. The product inside was not just food, it was a piece of reliable, predictable reality. The colour, a uniform pale yellow, was the same every time. The texture, smooth and yielding to a pocket knife, was unchanging, and the taste, mild, salty and rich with milk fat, was a consistent and knowable sensation. In a world where survival was a moment-to-moment variable, the cheese was a constant. It tasted the same in a muddy trench in October as it had in a stateside mess hall in May. This absolute predictability was not a culinary failure. It was its most profound psychological strength. This effect was not merely a matter of nostalgia, the proverbial taste of home. It was something more fundamental. The cheese functioned as a cognitive anchor. Every other element of the soldier's life was a descent into the primitive and the unpredictable. The Kraft tin, by contrast, was an artifact from a different world, a world of science, industry, and rational control. It was a tangible link to an American system where things were manufactured, standardized, and made safe. Opening it was an act of reconnecting, however briefly, with a society defined by order, not chaos. The psychological boost was inseparably linked to a physiological one. The high concentration of fat and protein provided a dense, satisfying caloric payload, a tangible feeling of warmth and energy that directly counteracted the cold and exhaustion of trench life. This feeling of satiety was itself a powerful contributor to morale, a bulwark against the despair that gnawed at an undernourished and physically depleted soldier. The cheese was therefore a dual-purpose weapon. It fed the body, but more importantly, it provided a small, consistent, and scientifically engineered dose of certainty in a world that had none. It was a taste of a rational universe, sealed in a can. When the armistice was signed in November 1918, the story of Kraft's processed cheese did not end. It entered a new and decisive phase. The 6 million pounds of product shipped to the American Expeditionary Forces were not merely a line item in the history of military logistics. They represented a dual-impact event that would reshape the American commercial landscape for the next half-century. The first impact was financial, an injection of capital that would give the company an insurmountable head start. The second was psychological, a mass-scale conditioning of the American consumer that constituted the most effective marketing campaign in history. The US government contract had served as a state-sponsored venture capital fund. The profits from the massive guaranteed order were not simply absorbed as revenue, they were reinvested into a war-financed program of industrial expansion. While competitors were still grappling with the high-risk, low-margin economics of natural cheese, Kraft was building new factories, perfecting its machinery, and streamlining its supply chains with a scale of investment that private markets would have never supported. The company emerged from the war not as it had entered it, a clever but speculative enterprise, but as a fully realized industrial powerhouse, its production capacity forged and battle-hardened by the demands of a global conflict. Simultaneously, the war had solved Kraft's single greatest post-invention challenge, market creation. The nearly 2 million American men who served in France returned home not as strangers to this new food, but as its most experienced consumers. They had relied on it for survival. They associated its taste and texture with sustenance and, most critically, with a predictable pocket of American order in a world of European chaos. They were a pre-built customer base, 2 million strong, who trusted the product implicitly and understood its value proposition instinctively. The post-war market was not something Kraft would have to conquer. It was a market that was coming home to them. The reverberations, however, extended far beyond a single company or product. The unqualified success of tinned processed cheese was definitive, battlefield-proven validation of a radical new industrial philosophy. It demonstrated with terrible clarity that a traditional biological foodstuff, perishable, inconsistent, and tied to the cycles of nature, could be systematically deconstructed by chemistry and reassembled by machine into a new, superior industrial form, stable, uniform and immensely profitable. The lesson was not lost on the broader food industry. If cheese could be tamed, so could anything. A new gospel of food manufacturing had been written and proven in the trenches. The industrial reformulation of the American diet had begun. The ultimate significance of Kraft's invention was not financial or even logistical, but philosophical. It represented a fundamental victory of industrial science over the perceived limitations of nature. For millennia, food had been governed by the immutable laws of biology: maturation, decay, and seasonal variation. These were not seen as flaws, but as inherent properties of existence. Kraft's process represented a new doctrine, one that viewed these natural tendencies not as realities to be managed, but as inefficiencies to be conquered and eliminated. The system he created did not just slow down spoilage, it achieved a state of near-perfect chemical stasis, lifting the product entirely out of the biological life cycle. This was not a truce with nature, it was a declaration of unconditional surrender, enforced at the molecular level. This victory of science enabled a parallel victory of industrial logic over artisanal tradition. The very qualities that a cheesemaker valued, the subtle character of a specific place, the unique complexity developed over a long maturation, the variation from one wheel to the next, were redefined by the industrial mindset as catastrophic failures. Character was an uncontrolled variable. Maturation was a countdown to loss. Variation was the enemy of the brand. The new ideal was not the creation of the perfect instance of cheese, but the infinite replication of the identical one. Perfection was subordinate to predictability. The 5-pound loaf was therefore more than a product. It was a manifesto, arguing that the highest virtue of a foodstuff was not its taste or its heritage, but its absolute unwavering consistency. With these victories, Kraft's invention did not merely create a new product, it created an entirely new category of substance, the processed food. Prior to 1916, food was either fresh or it was preserved, meaning it was salted, smoked, canned, or dried, methods that arrested decay but did not fundamentally alter the food's internal structure. This was different. This was a process of deliberate deconstruction and chemical reassembly. The final product's identity was derived not from its agricultural source, but from its method of manufacture. It was the first true food of the factory, an object of engineering, not of agriculture. A new kingdom of food had been established, its founding principle proven in the trenches and now ready to conquer the American kitchen. The pronouncement from the trenches was therefore absolute. The success of Kraft's tinned cheese was not the victory of a single product. It was the battlefield validation of an entire industrial worldview. The war effort had proven, under the most brutal conditions imaginable, that the foundational principles of this new science were sound. It demonstrated that a biological substance, with all its inherent unpredictability and fragility, could be systematically disassembled at the molecular level and re-engineered into a new form, one defined not by its agricultural origins, but by the logic of the factory. The result was a substance possessing absolute stability, perfect uniformity, and unprecedented logistical efficiency. The philosophical argument laid out in Section 22 was no longer a theory. It was now a proven doctrine, underwritten by government contract and confirmed in the crucible of global conflict. This victory marked a definitive and irreversible turning point in the history of food. The principles of chemical deconstruction and industrial reassembly, first perfected on scraps of Wisconsin cheddar, would not remain confined to the dairy industry. The success of processed cheese served as the foundational blueprint for a new generation of food science. It established a new set of tools, emulsifiers, stabilizers, preservatives, and more importantly, a new way of thinking. The objective was no longer to simply preserve food, but to fundamentally reformulate it, optimizing it for shelf life, consistency, and manufacturing cost. The factory, not the farm, would now dictate the texture, flavor, and physical properties of a vast and growing category of what Americans ate. The paradigm had shifted. The age of artisanal variance was ending. The age of industrial replication had begun. This was the ultimate legacy of James L. Kraft's war against spoilage. The initial problem, a simple matter of profit lost to mold on a Chicago wharf, had culminated in the creation of an entirely new kingdom of matter. It established a clear and powerful precedent that nature was no longer the source of food's final form, but merely the provider of its raw materials. The battle had not just been won against microbes and enzymes. It was a victory over the very concept of biological limitation itself. A new industrial gospel had been written. Its first chapter was cheese. The rest of the 20th century diet would follow.